Previously, we have seen selection combining, and we have also seen the expression of probability of fade in case of selection combining. So which was given in this form. It shows that the combined SNR is less than gamma TH if the probability that gamma 1 is less than gamma TH, or probability that gamma 2 is less than gamma TH, and so on. And since these all branches, they are independent, we can directly multiply the probabilities that gamma 1 is less than gamma TH multiplied by probability that gamma M is less than gamma TH. And then we arrived to this expression 1 minus e raised to power minus gamma TH upon gamma bar raised to the power M. And this M is known as the diversity factor. And when this is not comparable, when this gamma bar are not comparable, then instead of raised to the power of M, we can directly write M is equal to 1 to M 1 minus e raised to power minus gamma TH of gamma bar. And if this gamma bar is same for all the branches, then we can write this form. And also we computed the mean SNR in case of selection combining, and we have seen that the mean SNR is equal to the gamma bar multiplied with the summation over all the elements at the receiver. And we have seen that this, as we increase the number of antennas at the receiver, this mean SNR will always increase, because in case of when M is equal to 1, then we have gamma bar 1 plus 1 by 2. And when M is equal to 2, in that case we have gamma bar is equal to 1, in case of 2, when we have M is equal to 3, we have 1 plus 2 plus 1 by 3. And there is always an increase in the mean SNR when we increase the number of antennas. But still there are cases in selection combining when we have trouble, and that is when both the signals, let's say this is the first signal. The case is when both the signals, they are in fade. So this is the region, if this is the gamma TH and this is the first signal and this is the second signal. So there is a case when both they are in fade. So how we can see this? So this is the trouble when we use selection combining. So we'll see it later. So there are certain cases, let's say under strong signal conditions, when this gamma bar is very, very greater than gamma TH. In this case, exponential, this x will be small because x is written as gamma TH upon gamma bar. When this is greater, this value will be very small, and then e raised to power minus x can be approximately written as 1 minus x. And so as a result, we will get mean SNR, probability of fade equal to gamma TH upon gamma bar. And when we have M antenna, it will be raised to power M. So as we are increasing M, this probability of fade will decrease. Now there is another case. What if one of the M antennas is weak? From the M antennas, let's say gamma 1, the SNR corresponding to the first branch is very, very less than gamma TH. So how we proceed with this case? So if we solve this expression, we will get 1 minus exponential of minus gamma TH upon gamma 1. And since this value is very small and e raised to power negative of large number will be approximately equal to 0, and we will get this term gamma TH upon gamma bar 1 minus 1. And this means that effectively with the selection combining, if there is one antenna that is weak and the SNR corresponding to that antenna is less than the threshold, so the selection combining will act as if only we have m-1 antennas at the receiver. It will just discard the antenna that will have weaker gain. Now there are certain scenarios where the selection combining is not useful. The first scenario is one of the two antennas is weak, which we have said earlier. If one of the antenna is weak, then it will only select the signal corresponding to the first branch. And there are cases if the antennas are in correlation. When the antennas are in correlation and one of the branch is in deep fade, then the other branch will also be in deep fade. So we will look at, is there any benefit of this scenario or not? So in case of selection combining, this is a figure showing the CDF of normalized SNR versus the normalized SNR. So this is given by gamma upon gamma bar is less than abscissa. Probability that gamma by gamma bar is less than abscissa. So now what to look for in this plot is that, let's say we have this gamma is equal to -10. So probability that it will achieve -10 in case when we have one antenna at the receiver will be 0.1 probability. So there is a 0.1 probability that it will be in fade. Whereas when we increase the number of antenna, this probability has now reduced to 0.01. And if we further increase the number of antennas to 3, it will further reduce approximately to 0.01. So this is what we have seen, that as we are increasing the number of antennas, the M factor that was in probability of fade will increase and the probability of fade will decrease, and we will have a benefit of selection combining when we increase the number of antennas. And this dashed line here shows the optimal combining, and the optimal combining is known as the maximum ratio combining. We will see that in the later videos. Now we have certain scenarios. The first scenario is the noise limited scenario. When it is noise limited scenario, and if gamma 1 is less than gamma threshold, gamma 2 is also less than gamma threshold, that means the scenario which we considered above, in this case both the gamma 1 and gamma 2, they are less than gamma th, and there are scenarios where it is in deep fade. So selection combining is not useful in this case of scenarios, but there may be the cases that what if we sum this gamma 1 and gamma 2, then maybe the sum of gamma 1 and gamma 2 will increase the mean SNR and will take it greater than gamma th. There may be possibility of this. So whereas in the second scenario, that is interference limited scenario, in this scenario we have C over N plus I. So interference limited, we have a lot of interference, noise is very less compared to the interference. We can write it in this form, C by I. So now if we have a signal corresponding to the first antenna, that is given by H1S plus I1I plus noise, and we have second signal corresponding to the second antenna as I2I plus WI. And when we talk about strong antenna or weak antenna, what we mean by the strong antenna is the gain of the antenna. And weak antenna also means the gain of the antenna. So that means if the gain is high, we have strong antenna, and if the gain is low, we have weak antenna. So then if we compute C by I corresponding to Y1, this C by I corresponding to antenna 1, So this will be the ratio, and this one, since it depends upon the gain of the antenna, and the gain of antenna is similar for both the cases, they will cancel out each other. And similarly for Y2, the gain of the antenna will cancel out, and what we will have is that C over I of first antenna is approximately equal to C by I of second antenna. So when we talk about antenna diversity, what we have to look for is that the strong antenna, we have to look at the strong antenna that will provide us high gain. And second is both the antennas should be uncorrelated, or the M antennas, they should be uncorrelated to each other. When there will be correlation, if one is in the deep fade, the other will automatically be in the deep fade. So now the question is, why do you take trouble while selecting this signal? You are selecting the signal in selection combinings. We have one gamma 1 and we have gamma 2, and we are selecting which one is higher. And there are cases that we have seen that when this gamma 1 is less than gamma TH and gamma 2 is also less than gamma TH. So in this case, we are in trouble. But why not? If we just add up the two signals, gamma 1 and gamma 2, then there may be the case where gamma 1 plus gamma 2 is greater than gamma TH. So this implies if first signal is in deep fade, maybe the second signal will pick you up and the overall signal strength will be greater than gamma TH. So in the next video, we will continue our discussion with why not to simply add the two signals instead of just selecting the signals. What effect we will see when we just add up the two signals.